Hi, I'm Ryan Gibson, and I wanted to think about how a stale calibration of a tail risk model has an impact on model performance. So, the background here is that we're often asked to create risk models that forecast out a confidence interval of where future prices will go. In a credit risk context, really, I'm mostly concerned about this higher profile. An increase in price would represent money that a counterparty might owe me on a long trade here. And that would be money that I wouldn't get if they defaulted. So that's the money at risk in a counterparty default scenario. And so in general, we have a lot of historical data and we've chosen some sort of stochastic process. We calibrate the process and we use it to forecast out this confidence interval. And ideally, that gets recalibrated very frequently. But in practice, you often have to adhere to technology release schedules, or recalibrations might be delayed or canceled due to a tech freeze or maybe a technology system issue. And I wanted to think about how model performance is impacted because of that sort of stale calibration, either a release delay or not being able to recalibrate as frequently as you would want to. And so for everything in this presentation, I'm using a T-Levy process, and I'm focusing on 2-week price changes as a typical margin period of risk. The T-Levy process really just means that I'm modeling daily changes of the log price of the asset as IID samples of a T distribution. You can think of this as basically geometric Brownian motion, but fatter tailed. And if that degree of freedom parameter nu gets taken to infinity in the limit, this becomes a normal distribution, and so geometric Brownian motion. We find these parameters through calibration. And what I'm using here is just maximum likelihood fit to historical data. But as shown here, it's equally weighted. So this histogram is just historical data, and I'm fitting a t-distribution to it to recover these mu, sigma, nu parameters. That's not ideal. We would want to weight more recent data more heavily than older data, because the recent history is obviously more indicative of the near future than older data. And so we don't actually do this. What we do is we use exponential decay flexible probabilities so that our estimation becomes maximum likelihood estimation, but the data is weighted by these decay curves. I have two shown here because what really happens is you choose a half-life and then your probabilities decay by 1/2 each half-life. In my case, the degree of freedom is decaying by half once every year, 252 trading days, and the other parameters of the t-distribution are decaying once a quarter, 63 trading days. Now, this in general is a trade-off between how responsive you want the model to be to recent events and how stable you want the model to be, how stable you want the model parameters and the risk estimates. In my case, over a number of stocks, I found that this has a good level of coverage. Like the 95% and the 5% profiles are reasonable. They're actually reasonably accurate, and the parameters are stable, stable enough at least. One other thing I'd like to note is that this degree of freedom parameter really has to be larger, much larger than the other parameters, just because estimating the degree to which a tail is a fat tail is much more difficult than trying to estimate drift or a volatility, that sort of thing. So once we do this calibration, these are the parameters of nu and sigma that I'm seeing. And you'll see that temporarily ignoring like a COVID impact, this is quite stable. There are long periods of time where you're really within, 3.5 to 4 on the degrees of freedom. Your volatility is like within 1.4, 1.2%. So overall, this is relatively stable. And then these large jumps are pretty explainable simply because COVID, for example, was a very extreme market event. And that gets absorbed into this calibration as a fat-tailed event. It tends to increase the fatness of the tails. And so the degrees of freedom drops quite significantly. This particular example that I'm showing here is Eli Lilly, which is a pharma company, hence why this impact during COVID was a bit larger than in some other stocks. Now, I want to be able to talk about what these parameter changes do to model performance. And so I'm going to have a quick aside into model performance discussions. Really, with this sort of model where we're just projecting out the prices will stay below this profile 95% of the time, it becomes quite simple to just do a binomial test where you'll say, okay, if prices were supposed to remain below that profile 95% of the time, how often did prices exceed it? And if it's, significantly more than 5% of the time, probably your model is doing a bad job. So all this looks like is that we take historical exceedances of our predicted confidence levels and we calculate a binomial CDF with the number of data samples we have and the desired confidence level. So obviously, as you have more and more exceedances, the p-value of that statistical test will decrease and decrease. And at a certain point, you'll reach some a priori threshold of, say, 1%, where you declare, yeah, this model is not accurately predicting the tail risk. It has an issue. It needs to be investigated, needs to be enhanced, etc. And importantly, this really starts to become a metric of its own rather than like a proper statistical test. Model performance teams and people in the business will speak in terms of backtesting p-values just because it's how the model's performance is judged. Not really looking at it as a statistical test, but really a monitoring metric of model performance. And so it would be nice if we could discuss the stale calibration impact in terms of this sort of p-value. And one thing that we can do is that we can try and backtest the model against itself. One version with stale parameters and one version with newer parameters. This is intended to be, a very clean theoretical situation, which we're isolating away all model insufficiencies and we're just looking at the impact of the stale parameters. So to say that again, you have a stale model and you're using that to estimate tail risk. And then you are drawing simulated data from a newly calibrated model and you're using that to backtest in the backtest with the stale model. So over here on the right is what the p-values of the backtest look like if I do that on Apple right before and after the COVID crash with about a month of staleness in between. And you'll see that the threshold I said earlier of 1% is really appearing like 2.5% of the time. If your threshold were 5%, it would be, almost 10% of the time. So in that sense, your model is 2.5 times worse at passing backtesting than it really should otherwise be, assuming that your model is perfect. Like this is a backtest relative to the model itself. So everything else is isolated away. And what this means is that the impact of the stale calibration is effectively a shift in the failure threshold. It's almost as though you're doing the backtest with a failure threshold of 2.5% instead of 1%. And this is obviously just picking one particular stress scenario, but another thing that you could do is you could extrapolate out historical trends of how the calibration parameters have moved over time. This is again Apple, where I've taken some average moves of the parameters historically and then just kind of extrapolated that month over month in order to perform the same backtesting analysis, stale calibration versus new calibration. Now, it is worth taking this with a massive grain of salt because there's a lot of assumptions going on here. I'm assuming that your parameters are trending in a direction that makes your risk estimate worse. Fatter tails, higher drift, higher sigma. And I'm assuming everything's independent. I'm literally projecting out with those averages for each parameter. But with that grain of salt, you can see that staleness over the course of 3 months starts to make the model maybe twice as bad at backtesting as it really should be in a perfect world. But if you ever, for some reason, got out further than that, the performance of the model tends to get really, really bad, 6 or 7 times worse than it should be in practice. And now, of course, this is a pretty rough analysis, but anything further than this wouldn't often be focused on, simply because if you're trying to make a model better, you focus on the model. You don't tend to model out the calibration process itself. But this sort of back of the envelope estimate lets you speak about the impact in terms of the model performance metric, in terms of the backtesting p-value. And I hope that helps in kind of bridging the gap between what we would think of on the model side and what risk officers and model performance teams might think of just in terms of the backtesting metric itself. Thanks.